Hello, Jan.
Yeah, thank you very much for the kind introduction and for having us here today at this great meeting. I see there are already 100 people online who can now witness the first official presentation of Twin Photonics. I'll be talking today about empowering quantum photonics with turnkey integrated quantum sources, and I want to quote Dimitri on here. Um, we all need light for our quantum applications. And in some cases, this can be quantum light, and in some cases, this can be laser light. And we want to fill this niche of quantum light here today. So a lot of you are probably familiar with the quantum internet idea, where we have the classical internet for our classical data infrastructure, and where we have the quantum internet. And the quantum internet is useful for things like quantum key distribution and distributed photonic quantum computing. And all of this relies on the idea of broadcasting entanglement in some shape or form. And if two parties are far enough apart, then usually light is the medium that you want to use to connect these and share entanglement between the two. Um, and with that comes our offer. We are offering entangled photon pair sources that are turnkey. They are based on a similar technology as the HELAS lasers. They are fully integrated and fit into a butterfly package. Right now, our sources emit in the C band, so around 1550 nanometers, and are frequency tunable, so you can choose your preferred degeneracy point. They provide heralded single photons that are multiplexed in frequency. You can see here on the bottom right in this little diagram. So we'll have a degeneracy point in the center where we have a laser, and that produces photon pairs through spontaneous four-wave mixing. So you will get one photon of the two at a higher frequency called the signal photon, and one photon of the two at a lower frequency called the idler photon. Yeah, and by detecting one, you basically herald the existence of the other one. Um, Additionally to just heralded single photons, they also provide entanglement in frequency bins, and also soon, once we finish development on that, in time bins. And these entangled photon sources have a fully European supply chain as well. The interesting thing here about the time bin and frequency bin entanglement is that compared to standard, what you might already know, polarization entangled sources, these both are scalable, meaning that you can have many, many basis states. So in the frequency domain, you can think about just placing more and more laser frequencies or optical frequencies next to one another. And each of these frequencies counts as a basis in quantum information. And in the time domain, you can do the same by just placing pulses of photons next to each other. And then within your information transfer window, as many time bins or frequency bins as you can fit in there, the higher dimensional your encoding will be. And the higher dimensional your encoding, the more information you can transmit in each send operation. Additionally, the frequency domain is easily multiplexed. We all know in classical communications, we have just passive wavelength division multiplexing splitters. And these allow for easy multiplexing and sharing of light between different parties. And in the time domain, they are very, very easily interfered because you can just build interferometers where you delay one part of the light by a so-called one-bit delay, meaning that you overlap two pulses that are usually adjacent in time at a common time. And this allows you to get out the interference pattern very, very easily. Right. We also have a prototype that arrived just the end of the beginning of December. It's already turnkey, and it's a hybrid silicon nitride and indium phosphide integrated design. It's fully packaged in a butterfly, and it's with driver electronics. And we've had it stable over many, many weeks now. So we got it to work immediately after it arrived here. The hardest was really just plugging in the power, and photons came out already. Yeah, the design you can see in the bottom left here. So it's similar to what Dimitri shared about the HELAS lasers. We have an indium phosphide waveguide as a optical amplifier, and then three ring resonators and a mirror with a tunable output coupler. And these ring resonators, similar to the HELAS lasers, are used to set the laser wavelength. But additionally, we are also using the ring resonators because they provide intrinsic field enhancement to produce a quantum frequency comb in one of the rings through spontaneous forward mixing in the silicon nitride. Yeah, and that one we can couple out, and we have measured that, and you can see it here on the right-hand bottom side. So this quantum frequency comb is spanning 4 modes of each a signal and an idler photon, with more than 25,000 photon pairs per second at the device output, and a CAR of more than 40, which is the quantum equivalent of the signal-to-noise ratio of the photons that you detect. Our new future goals are to develop this quantum source into a full-fledged C-band spanning source where we have a dense mode spacing of 25 to 50 gigahertz. Our current source has a mode spacing of 200 gigahertz, where we have many entangled modes. So we are targeting more than 50 modes spanning then the C-band. Ultra-high photon rates at about 50 to 100,000 photon pairs being generated on each mode every second, and also time-band entanglement for QKD applications. Yeah, and as Dimitri also said, wherever there's gain, we can build a laser. Wherever there's gain, we can build such a quantum source because the design is pretty much center frequency agnostic. So we can think about 1.3 micron fiber communication in the O-band, which is currently a very hot topic in research because that is one of the frequencies that you can use to still communicate over actively used classical telecom networks, because in the C-band there are a lot of channels that basically pollute the other channels with stray light. And at 1.3 microns, there are specific channels that you can use to that are very, very low noise. So you can still transmit your quantum data on them without having too much noise from the classical signals. We can also think about satellite communication in the between a base station and a satellite, and also near infrared atom and molecule interaction with sensing and many, many more applications. So for example, if you have 2 atoms or ions acting as qubits and you want to entangle them at a distance, you would need entangled light to share then entanglement between the 2 atoms. And this is also something that we can do in the future. These wavelengths are really customizable to your requirements. So let us know if you have a favorite wavelength where you would like entangled light, and we can talk about making that happen. Lastly, who are we? Twin Photonics. We are a very, very young startup originating from the Quantum Photonics Research Group at Leibniz University Hannover in Germany. Together with my Professor Michael Kues, we founded this company just 10 days ago. Yeah. And what are we looking for here in EPIC? So your use case, mostly get in touch with us. Let's talk about your requirements for quantum light. We're also looking for feedback on our prototypes. So you can get a virtual lab demonstration, but even better would be if you random purchase one of our prototypes to test it in your lab and give us feedback on our source. And lastly, we are looking also for high isolation fiber optic filters to suppress this pump light that we use to generate the photon pairs in the microring. There we are currently investigating chip integration, but for now it's a lot more convenient to use just passive fiber optic filters to block out the pump light because it's a lot more repurposable. And with that, thank you very much for your attention. Get in touch with us, write us an email, follow us on LinkedIn where you get more information on our releases, also information on our website release, and additional communication channels once we have an email set up. Yeah, thank you very much.